Objective 12.1, the fundamental counting principle and permutations. In this objective, we want to be able to use the fundamental counting principle to count the number of ways an event can happen. We also want to be able to use a particular procedure called permutations to count the number of ways an event can happen. So let's take a look at an example. Suppose you own a small deli. You offer 4 types of meat: ham, turkey, roast beef, and pastrami, and 3 types of bread: white, wheat, and rye. How many choices do customers have for a meat sandwich? Well, one way you can deal with this is to actually plot it out, and we can do that best with a tree diagram. You can see here that initially you have 4 choices based on the type of meat you want, and then for each of those meat choices you have 3 choices as to what type of bread you would want. And so then you could figure out how many different possible sandwiches you could make by using the diagram. However, using the tree diagram can be a bit tedious, especially when you have lots of choices and lots of options for each choice. So instead of having to draw it out, we want to use something called the fundamental counting principle. Now this is already printed for you in your guided notes because it's a rather wordy explanation, but I wanted you to have it there to look at in case you needed reference later. It basically says this: if you have 2 events, the fundamental counting principle works if one event can occur in m ways and another event can occur in n ways. Then the number of ways that both events can occur is m times n. So as an example here, they're telling you if one event, sorry, there should be a T there, if one event can occur in 2 ways and another event can occur in 5 ways, then both events can occur in 2 times 5 or 10 ways. And then you can expand that to 3 or more events by multiplying out all the possibilities. So we can use that in our deli situation. We have 2 choices to make a sandwich. We have a meat choice and we have a bread choice. According to the fundamental counting principle, my first event of choosing meat can happen in 4 different ways. I have ham, turkey, roast beef, and pastrami. My choice for bread, the second event, can happen in 3 different ways. I have the choice of white, wheat, or rye. So the fundamental counting principle simply says I can take these 2 numbers and multiply them together in order to find out my total number of choices. So the way that both meat and bread can happen, the number of ways that can happen, is 12. There are 12 different possible meat sandwiches. This is a whole lot easier to set up than drawing a picture every time you want to figure out the number of ways. Okay? So let's take a look at an example where we could use this. In this example, I've given you 3 examples of license plates from the United States. Let's assume, for purposes of our problem, that all license plates in California follow this basic configuration, where it starts with a digit, and then it has 3 letters, and then it has 3 digits. Let's assume all license plates in Iowa follow this configuration of 3 digits followed by 3 letters. And in New York, let's assume that all of the license plates start with 3 letters and are followed by 4 digits. Okay, so my question is, how many different license plates are possible in New York if letters and digits can be repeated? So in New York, we have 1, 2, 3, 4, 5, 6, 7 spots that need to be filled with either letters or digits. So I have given you 7 blanks here, that we want to fill in. And sometimes I find this easier to actually just put in the blanks to represent the choices that I'm trying to make. Helps to keep things organized a bit. Now in the first spot, since my first 3 spots are letters, how many choices of letters do I have for this first spot? Well, there are 26 letters, so I have 26 choices to put in that first place. Now what about for the second spot? Again, the second spot is a letter spot, and according to my directions, I can reuse letters and digits. So that means that for both of my remaining letter spots, I still have 26 choices that I can make. Now when I get to my next spot, I'm choosing a digit. So I have to decide how many digits can I choose from to put into this spot. And since 0 is also a possible digit, I really have 10 digits to choose from. And again, because any of the digits can be repeated, the rest of my digit blanks will also have 10 to choose from. So now, according to the fundamental counting principle, I can just multiply all of these together and get an answer, which is about 175,670,000 different license plates that could be created in New York using this configuration. Okay, let's try another question. How many different license plates are possible in California if letters and digits cannot be repeated? So now our first blank has to be a digit. And since it's our first blank, we still have 10 digits that we can choose from. Our next blank is being taken by a letter, and so since it's my first letter blank, I have 26 letters to choose from. But now when I go to my next blank, if I'm assuming I cannot repeat letters, then that means whatever letter was chosen here is no longer an option. So that leaves me with only 25 letter choices for my next blank. And then that would be true as well for my next letter blank. I would only have 24 choices because I already have 2 letters that have been chosen. Then I get back into digits, but since 1 digit was already chosen for my first blank, I only have 9 digits left to choose from for this blank. And then continuing with that problem on our last 2 blanks, I would have 8 digits and then 7 digits that I could choose from. So I have to be more careful when I cannot repeat things, because once something is chosen, it's no longer part of my choices in succeeding blanks. Alright, so now that I have all my numbers in place, I can again apply the fundamental counting principle, multiply all of those numbers together, and I get 78,624,000 different possible license plates. Okay, now a particular type of fundamental counting principle is called a permutation. And a permutation is simply a situation where you are trying to order objects. So there's a particular order that you want. You're trying to figure out how many ways you can get things in that order. That is a permutation of objects. So here's an example of a problem where that might be the case. You have 12 skiers who are competing in the final round of the Olympic freestyle skiing aerial competition. In how many different ways can 3 skiers finish first, second, and third to win the gold, silver, and bronze medals? And we're going to assume that there are no ties. So this is an example of a permutation because we are trying to order objects. It does make a difference what order the people are in. For example, I might have 3 people, Amy, Bob, and Carl. And having Amy win the gold, Bob win the silver, and Carl win the bronze is a different result than if I had Bob win the gold, Carl win the silver, and Amy win the bronze. Even though it's the same 3 people, the order of them makes them different results because they're going to win different medals. Okay, so the order does make a difference in this case, and that makes it a permutation. So with permutations, we have a certain notation that we use. We have a capital P, which has 2 subscripts on either side of it. In this case, we have a 12 to the left, and we have a 3 to the right. And the way this is read is we say this is the permutation of 12 objects taken 3 at a time. So it's n objects taken r at a time. In this case, that means we have 12 objects, which would be the skiers, and we want to order 3 of them to get gold, silver, and bronze. So this is how we would write the permutation for that situation. The formula for a permutation says that n objects taken r at a time can be found by taking n factorial, that's what the exclamation point means, it's factorial, over n minus r factorial. Now factorial is kind of a strange creature here, but it is useful because it's a button that's on graphing calculator, so sometimes you can just put it into a calculator if you need to. What factorial means is that if I have n, then I'm going to take that times 1 less than n, and then times the next number, whoops, try that again, the next number less than n, so n minus 2, and then so on until I get down to, try again, taking 3 times 2 times 1. So you're just listing out all of the numbers from n down to 1, and you're multiplying them all together. That's what n factorial means. Okay, so in this particular case with our skiers, we're talking about 12 objects being taken 3 at a time. So that means I need a 12 factorial on top, and then 12 minus 3, which would be 9 factorial on the bottom. Now technically what that means, 12 factorial means taking 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and then 9 factorial would do the same thing starting with 9 all the way down to 1. But notice what happens. From 9 down to 1, I have common factors. Since they're all being multiplied, it makes them all factors. So they're going to cancel each other out, and all I'm really left with to multiply is this 12 times 11 times 10 right here. And 12 times 11 times 10 is 1,320. So there's actually 1,320 ways that the gold, silver, and bronze could be won in this competition. Okay, let's take a look at one more example like that. Let's say 2 of the skiers were injured, maybe during the warm-up round or preliminaries, and so now only 10 skiers are going to compete in the final round. Sorry about that typo there. So now how many ways can the medals be won? So now we're talking about 10 objects being taken 3 at a time, because the medals are still going to make a difference what order, so we're still using permutation. So we have 10 factorial on top, and now we have 10 minus 3 factorial on the bottom, and then it is the factors from 7 on down that will cancel each other out. Oops. And so what I'm left multiplying is 10 times 9 times 8 9 times 8 is 72, times 10, 720 ways out of 10 skiers. Alright, so you may have noticed now that I haven't given you any guided practice. This is part of the change for this chapter that I want to try. So hopefully you got to this video through the Mentor Mob website. It should have been the first step on the website. Now, if you go back to the Mentor Mob, or if you're still in it and watching this video within it, your second step is going to be a quick quiz that's going to ask you some questions related to the information and the examples I've just given you. The nice thing is, when you answer these questions, it will give me a report on my teacher page so I can see how you're doing and whether you're understanding or not. So, your next step is to go to the 12.1 quick quiz, which is the next step on your Mentor Mob. Those will be your guided practice problems now. And then, once you've done that, you can start working on the 12.1 practice to get it completed. And then once everything in Objective 12.1 is complete, you can get it checked off by me. If you have any questions about this new setup or about this lesson, please make sure you ask during class. We'll see you next class.